Let's talk about numerical integration. Integration just means putting things together. Let's say I have three areas and I want to add them together. I'll just add them up. Simple enough. And this idea can be used for more complex problems. Let's say I have something more complicated, like finding the area under this curve, y equals cx squared. I can approximate that area by using a bunch of rectangles. Here we have 5 rectangles. How do we figure out the area of each one? We can take the height and multiply by the width, which I'm going to denote as dx, a small interval of x. Multiplying the height times the width would give us the area, which we'll call dA to represent a small area. To get the total area, we have to add up all the little areas. In a computer program, we can keep a running total by using the next line. This says take the value of the area that we have so far, add the new area of our newest rectangle to that area, and then store that information back where we're keeping our area. And we're going to keep on doing this down the line as we go from one rectangle to another. So these 3 lines form the core of our concept for numerical integration as we'll perform on a computer. So on the left here, we have a summary of the problem. On the right, I'll lay out the computer code, starting with our summation statement that simply says we're going to keep a running total of all of the areas of those small rectangles. To calculate the little area, it's just y times dx as seen in the lower left rectangle. Each rectangle has an ever-increasing height given by y equals cx squared. These calculations need to be repeated over and over again as we move across to the right along x. We need to put these commands into a loop. In Quick Basic, we have a loop command called for next. The initial statement is for I equals 1 to n being the number of rectangles we plan on breaking the area up into. We close the loop with the next command. It tells the computer that we're going to increment I by 1. So I is going to count 1, 2, 3, 4, up to, let's say we had 5 rectangles. Let's put some parameters in. C is going to be 0.2. Let's say I want to find the area up to x equals 3. These parameters need to be defined. And let's say I break this area up into 5 rectangles. I have to say n equals 5. The only thing left to do now is to calculate the width of each rectangle. And the last thing we'll do is we will print out our answer. We'll print out how many rectangles we had and the area that we've added it all up to. Now you might say, what about those little triangles above the rectangles? Aren't we going to be missing those areas and it's going to cause an error? Well, of course, and just like in calculus, when we start increasing the number of rectangles, those little triangles start to get smaller and smaller, and then they will eventually just disappear. If you know calculus, you know that the area would be equal to 1/3 cx cubed, and we'll be able to check our answer against the calculus. And we'll put that formula right in the program and let it print it out too. Now you might notice that this is just the way we might write it on the board, but in the computer, you're going to have to use the asterisk for the multiply sign, and you're going to have to use the caret to raise the exponent. All of this has to have the asterisk for the times sign. And we're going to have to increment x. So I've got to squeeze it in right here. Of course, we need to make x bigger every time we move to the next rectangle. The area from the calculus, 1.8. What does the program give us? If we break the area up into 5 rectangles, we get a total area of 1.296, a substantial error. We break it up into 10 rectangles, and we have 1.539, getting better. 100 rectangles, 1.773. We're getting better. At 10,000 rectangles, I round off to 3 decimal places, and I get 1.800. Now you might say, why bother doing this if we can do the calculus? And the answer is that maybe the formula that we need to find the area under isn't so simple as y equals cx squared. In physics, we're going to run into lots of problems that are going to be much more difficult, and the numerical method of integration can really help us out. What are we making an assumption about this? When we use the value of y, we are assuming that it remains constant for a short interval. We know that it's not really constant, but it's an approximation that gets very good as long as the interval is short. It would be good to practice a few problems. Try modifying the program to find the area under y equals cx to the 1/2 plus y naught. Specify your own values of c, y naught, and x final. And then do the calculus and check your answer and see if you're getting the same thing on the computer program. Of course, the answer will get closer and closer the bigger the value of n. Then try y equals cx to the -1. And if you find the area under this, you're going to want to make sure that you start with a finite limit from x naught to x final that you can set yourself. Check that with the calculus as well. Then you'll be able to move on to a problem such as how long will it take a small mass to fall to the earth? That's a lot harder of a calculus problem, but modifying this program, it should be pretty easy.